So I'm the last speaker of today, and I'm speaking of mobility after Mirko. There is nothing interesting I can say to you to convince you, but please let's try to stay together for a moment. Yeah. So recommender systems again. What are recommender systems? I assume you know are the systems that provide us with a lot of suggestion on what to eat, which friends to make, where to go. In this case, in this presentation, we will focus on the urban mapping realm, and of course, we are not. There are plenty of application of recommender systems on the urban environment. Think about Google Maps that suggest you which route to take, but there are also recommender that tells you where to go. For example, Google Maps, the same Google Maps again, or I don't know, TripAdvisor or several of them. So in general, a next POI recommender systems is a system that takes in input a set of trajectories, builds this interaction matrix, and feeds an AI model or a mechanistic model or whatever that gives a suggestion on where to go next to an user considering its trajectories. So I always go to pubs and soccer fields. It's likely that I will go to pubs and soccer fields again. Of course, these are new systems, and once we know very well we try to know very well which are the effects on the cities of phenomena like segregation or venue popularity. We don't know if in the long run these systems will have some impacts on these topics, like, for example, the interaction with locals, fostering or not segregation, gentrification, or, for example, the amplification of some popularity of the venues. Well, this is the core question of today. So are these recommender systems of POIs, that is point of interest, affecting somehow the visitation patterns? This work is part of a broader line of research that is human AI evolution that was led by our lab, in which we focused on this problem, especially on the formalization on the feedback loop, right? So we continuously produce data. This data will be used to training algorithm. This algorithm will give us suggestion, and likely we accept the suggestions. And this will create this feedback loop that will go on with possibly unintended consequences. How we can study this feedback loop? Well, Gabriele already told us a bit of today. Ideally, we would like to have company algorithms and data, so to know which is the effect, testing it with some A/B test or other technique. But as you know, we live in a society, so companies are not that happy of giving you data or giving you algorithms. So what we try to do is to do a simulation. Unlike behavior on supermarkets or other retail system, we do know how people move. There are plenty of models that explain mobility, individual, collective. For example, for the individual mobility, we have a well-known model that is called the EPR, Exploration and Preferential Return, that postulates that one can model an individual mobility as a two-phase process. A phase in which I return to an already visited location, and a phase in which an agent or I can explore a new location. This is a function of the number of visited locations already, but let's keep it simple. It's a classical mechanism that tells you how an individual moves. This has been proved to be effective with a lot of papers expanded and blah, blah. Okay, so our idea is to embed this mechanism into a more sophisticated mechanism that could account the fact that the exploration of the cities nowadays is driven by AI. We constantly ask AI where to go, where to visit, which is the best restaurant near me, and these kind of things. So we propose this mechanism for which, with a probability 1 minus eta, I can do this autonomous choice. So I move according to the APR model. With probability eta, I follow the recommendation of a recommender system. Basically, what we do is to keep some Foursquare data that are data reporting visits to point of interest, and we create this feedback loop. So we train a recommender system, we understand which users have been active that day in the data, since we use as a training set only a certain time amount of data, and we go through this procedure. So we flip a biased coin and design how to explore, we update the training set, and we repeat this feedback loop for some epochs. Of course, when we visit, we never say Google Maps, please tell me where to go in a city. I need to have a category. So how do we estimate the category that we want to visit? We have it in the data. So what we do is to use as a training set the data up to a certain time, and then mask the actual place that the user visits, and only considering the category, mimicking a user asking for a recommendation. So the return phase is just a classical return phase. So I return to a place if the random process decided that I need to return. I return with a probability that is proportional to a number of times I visited that place. The exploration phase, the classical exploration phase, basically is quite similar. I pick a radius from the jump distribution, I select the POIs of the category I want to visit, and I choose the POI according to their relevance. We estimate relevance with a classical procedure that is done in literature. The most interesting part probably is the AI-driven exploration phase. So I ask the recommender system, I ask for a category. The recommender system, we implemented many of them, we will see in a bit, return me a list of k places belonging to the correct category, and I will choose among these places with a probability proportional to the score that the recommender gave me. This, of course, is based on the last training set that I have, because each epoch we update the training set with the new exploration we collected. Boring slide, we implemented a lot of recommender system, both collaborative filtering, both personal recommendation, AI approaches, geographical approaches, and as many as you want. So the main idea is in the recommender system community, usually we look at metrics like hit rate, accuracy. Here the idea is to look at the complex systems and to evaluate it both at an individual level, so how the complex system of individual relationships changes or is impacted, and the complex systems of the POIs, so how the points of interest visits change. Of course, we want to understand it with respect to the impact rate and eta. So we want to understand this effect, how does it changes with the approach, with the usage of the recommender system. Sorry, I already said that. So the first structure we introduce is that temporal is not really temporal, but it's easiest to think of it as a temporal collocation network. So in our process, we have a concept of time, that is the epoch. The nodes are the users, and the edges between two users are there if two users visited the same POI in the same epoch in the simulation. Actually, it's a collapsed temporal network. Time is just an attribute here. Well, temporal metrics are a good indicator of this. No, in the plots, if you study like the assortativity or the density is not clear. What is it clear is that when you study properties about rich clubs, so about the nodes that are more connected in this collocation network, well, it seems to respect a pattern, right? So the lowest the eta, the lowest the metric. What does it mean? That we can collapse this temporal collocation network into a single collocation network. So two users in this global network are connected if at least once in time they visited the same POI. And we observe the first result. So in general, all of the recommender system tends to reduce the degree exponent of the collocation network. What does it mean to reduce that the distribution of the degree of the collocation network start to be flatter? We will see it in the next slide better. And also we notice that if we pick a rich club, so the 15 or 20 more richer nodes in the network, the density of the graph induced by these nodes seems to increase up to becoming almost fully connected. Let's see an example. we also see two regimes. One is the one described by the deep learning based recommender systems, and one is the regime described by the item KNN recommender system. Item KNN recommender system is just an item collaborative filtering. So I suggest you items, in this case POI, similar to the ones that you already visited. Let's see an example. In red, we have the rich club nodes of the collocation network. Here we have the acceptance rate of the recommender system. In the case of the item KNN, the networks seem to be quite similar in terms of connection. But when we accept in the simulation all the time suggestions given by multiwire or other recommender system, these networks becomes nearly fully connected. And here is a visualization of the degree exponent that I told you before. Clearly, when we use the multiwire or the deep learning architecture of recommender systems that are the most likely to be implemented by companies, everybody seems to get more connections. This is a first clue of centralization of the visits. At the visitation layer, we focus on two types of Gini coefficients, a collective one and an individual one. Collective Gini means I take all the distribution to the POIs and I study how much unequal is this distribution. The individual Gini is that I take my distribution visit and I average it across all the users to understand on average at an individual level how does it change. And here we observe the first clear trend. So in general, all of the recommender system reduce the average individual Gini index, meaning that they foster creativity. If you assume that the number of POI is fixed, reducing the Gini index means that your distribution of visits is more equal, so you are exploring more. At the collective level, we observe the opposite result, even if some recommender system like item KNN seems to evenly reduce this Gini index. Let's see an example, a special example. This is the distribution of visits of cherry-picked users when we never accept the recommendation of the recommender system, and this is the distribution of visits when we always accept the suggestion of the recommender system. So as you can see, here we had two clear attractor, and here we had no attractor. I forgot to say that in the data we completely remove host and works from the data. So having these polarized patterns is quite strange. And as we can see, the more we accept the recommendation of our recommender system, the smaller this indicator. On the opposite, if we average the result for a bunch of 250 users, what we get is an increase in this Gini index. As you can see, here emerge some zones where all of the users are relocated. This doesn't happen when we use item KNN as a recommender system. So the pattern of here is quite respected, and even here, so this reduction is not present. Please don't be fooled by the fact that the y-axis is not the same as before, but it's quite stable actually. So some gap, we discovered that recommender systems tend to boost individual diversity, but they don't do so with collective diversity. So visits may concentrate on a few popular venues. Why we say may? Because right now we just demonstrated that they concentrate to some venues, not some popular venues. And they generally promote the mixing in the collocation network, but they also promote the fact that rich nodes tend to be almost segregated among themselves. I want to show you the last plot. This is the distribution of visits in the training set. As you can see here, the top decile in the training set gained 33% of visited venues. If we use the multi-device recommender system, this shares goes up to 56.91%. It means that the venues that are suggested the more, if we use a lot, if we have a strong confidence on the recommender systems, are the ones that were already popular. So we are experimenting a rich get richer dynamics. Concluding, we devised this agent-based model for POI explorations. We want to consider also AI suggestion, and the striking result is that the individual creativity increase while the collective exploration decrease. This is consistent with some studies that are going up in this period. For example, some modern scholar did similar experiments on the generative AI, discovering that even in the use of large language models, you seems to be more creative, but collectively we all go toward the same style of writing. And in this case, we also added rich get richer dynamics. This work is under final review at Machine Learning. We expanded it also to Tokyo, not only New York City. That was a bigger and more complex data set to analyze. We plan to extend it forward to other source of data, even if getting POI data is not that easy, but there are some other proxies. And of course, we want also to give a gift to LLMs online, so we release the open code, so they are free to train on ourselves. Of course, some limitation is a simulation. Validating simulation is not easy because this is a behavioral model, so even having correct data, one should ask, are you doing it because you trust recommended systems or not? And so it's hard to generalize. You can see the code and the paper online. If you have any question, I'm happy to address them.
Thank you, Giovanni.